And now we'll move on to solving systems of linear equations. We'll solve for two unknowns, for which we'll need two equations, as well as three unknowns, for which we'll need three equations. You'll hear me refer to these as 2x2 systems or 3x3 systems. So we'll start with systems of two equations that have two unknowns, or 2x2 systems. Generically, they look like this. We have some number, a1, times x plus some number b1 times y is equal to some number c. So here a and b are coefficients for x and y, and c is a constant. And our second equation similarly has the unknowns x and y, and a, b, and c are constants, or some numerical value. The solution to this system will be an xy coordinate pair. What does this represent? Well, we'll start answering this question by looking at solving these systems graphically. Here are our first two lines, our first two equations, our first system. We have two unknowns, x and y. So our solution will be a coordinate pair. To solve these graphically, let's first graph the lines 3x plus y equals -12 and x plus 3y is -20. To do this, I'll first rewrite both equations in y equals mx plus b form, so that I have the slope and the y-intercept and can easily graph them. I'll label these as equation 1 and equation 2, so we can easily refer to them. So for equation 1, if I solve for y, I get y is equal to -3x minus 12, which means that we have a slope, m, of -3 and a y-intercept, b, of -12. For equation 2, I'll give myself a little more room by writing it up here. We find that 3y is equal to -x minus 20, and dividing through by 3 gives me y is equal to -1/3 x minus 20 over 3. So here we find a slope that's also negative, but much shallower at -1/3, and a y-intercept of -20 over 3. Let's take a moment to graph these two equations. So I've graphed equation 1, the steeper line, and equation 2, a little bit crudely. For each tick mark on this graph, I've indicated that this takes up 2. So what do we find? There's an intersection point here, and it's at x is equal to -2 and y is equal to -6. What is that intersection point? Well, it's a point that lies on both equation 1 and equation 2. So this is the solution to the system. The solution is x is equal to -2 and y is equal to -6. So when we're solving a system of equations, we're solving for the point where the two lines intersect. For most of our systems, we will have a single intersection point. There are two exceptions to this. To explore these exceptions, let's look at a second example. Again, we'll look at these two equations, so I'll label them as equation 1 and equation 2, and we'll solve for y in both. So from equation 1, we have 2y is equal to -3x plus 5. Dividing both sides by 2 gives me y is equal to -3 over 2x plus 5 over 2. For the second equation, I have -4y is equal to 6x plus 5. Dividing through by 4, or rather -4 this time, gives me y is equal to -6 over 4x plus, rather, minus 5 over 4. Simplifying gives me -3 over 2x minus 5 over 4. Well, I find that while the y-intercepts are different, the y-intercept for equation 1 is 5 over 2, and the y-intercept for equation 2 is -5 over 4. So the y-intercept is where we cross the y-axis. The slope for both is -3 over 2. It's true for the first equation, and we see that it's the same in the second equation. Let's see what these two look like graphically. As you've probably already guessed, line number 1 and line number 2 are parallel. They have the same slope, but different y-intercepts. And here I'm using a scale of 1 gray square as a unit of 1. So our y-intercept for the first line was positive 2.5, and for line number 2 was negative 1.25. Because they have the same slope and this continues on in both directions infinitely, these two lines will never intersect. There's no solution to this system. So we simply give that as our answer. There is no xy coordinate that will satisfy both equations, that will give us a solution in equation 1 and equation 2. So there is no solution to the system. So far we've explored what happens when we have one solution, what it looks like when we have no solutions. There's one last one that we need to look at. Here's our final scenario. 2 equations, 2 unknowns. Let's put those on a graph. From equation 1, we find y is equal to negative 3x plus 10. And from equation 2, again, I'll take a little bit more space. We get 4y is equal to negative 12x plus 40. Dividing through by 4 gives me y is equal to negative 3x plus 10. So for both equations, I find that the slope is equal to negative 3 and the y-intercept is equal to 10. Just for fun, let's graph these two. Again, I've used a slightly modified scale here, but in any case, equation 1 and equation 2 have the same graph. They are the same line, or we can think of it as one line lies on top of the other. That means any point that I can find on line number 1, like this one for instance, 6, 8, is also on line number 2. And since there are an infinite number of lines or points in line number 1, there are an infinite number of solutions. So we say the number of solutions is infinite. We can summarize this as follows. If we find we have a system with a single solution, we call that system consistent, or we say it's an independent system. Generally, we'll just say, here's the xy pair that is the solution. If we have a system with no solutions, on the other hand, this happens because the lines are parallel, and we call this an inconsistent system. And if we have an infinite number of solutions, this happens because the two lines we're looking at are coincident, or the same line, and we call this a dependent system. Of course, solving a system of linear equations graphically is going to be both time-consuming and probably inaccurate in most cases. So we'll develop an algebraic approach to find these solutions.